Hello everyone, let us continue our discussion on reinforced concrete design. We are in week 7 and this is our first lecture. In this week, we are going to learn how to design deep beam. Now, let us first define the deep beam. As you have noticed from the beam design, for a given length, the depth of the beam actually dictates whether it is a deep beam or a shallow beam. Now, as per clause, in IS 456, the clause number is 29.1. For a simply supported beam, if the L effective by D, capital D, that is the total depth, not the effective depth, is less than 2, then it is a deep beam. And then for a continuous deep beam, the same ratio L effective by capital D is less than 2.5. You can see photograph of a deep beam. You can notice that this depth of the beam is too large compared to the normally designed beams, right? So this is a deep beam. And in fact, if you notice the steel provided in this beam, you can see we have here horizontal steels throughout the depth of this beam, right? This is not normal in case of a shallow beam. Recall, in case of a shallow beam, we do not normally have reinforcement in the compression zone so much as you can see here, right? Now, if you look at the deformed shape of a deep beam, you can see it here. So, for a simply supported beam, the dotted line shows the deformed shape and the central deflection here. I have already explained that to be a deep beam for simply supported, this ratio L effective by D should be less than 2, and the same ratio for continuous beam is less than 2.5. But for continuous beam, see this dotted line here, it shows the deformed shape. And here you can notice that there is a sagging moment here at the midspan. So this is the midspan, and there is hogging moment at the support, as opposed to only sagging moment at the midspan in case of a simply supported beam, right? Now, ideally speaking, a simply supported beam with UDL should have zero bending moment. So, no steel requirement here, but you can see from this diagram, there are a lot of steels there. So, how to design those steels is basically the theme of this discussion. Now, before that, we need to first calculate L effective, right? The effective span length. Now again, we have already discussed earlier during beam design. Let us quickly revisit the L effective as per clause number 29.2 is the minimum of these two options. So what is that? Center to center distance between the supports. So if we have say one support here, another support there, so we have to identify the center line of the support, and then that distance is the L effective, and the other option is 1.15 times the clear span. That means if we have a support having some width, so this is the support width, and we have another support on the other end, so it is the clear span between the two supports. Okay, 1.15 times the clear span is the L effective. The minimum of these two options we have to consider the effective length, right? So once the geometry is given, be it continuous or simply supported, we can identify the L effective, or that is the length we have to consider while we calculate this ratio. Now obviously for a continuous beam, because we have multiple spans, for each and every span we have to identify this L effective, and we have to check the condition for deep beam whether it is satisfied or not. The moment we will solve some example, it will be further clear to you. But what is the difference between the shallow beam and the deep beam? Recall, in case of shallow beam, we use normally Euler-Bernoulli theory, right? And the design of the shallow beam is started with the strain distribution, and recall that strain distribution over the entire cross section is linear. However, in case of a deep beam, when you move from here to there, the strain distribution across the cross section is no longer linear. So we have a strain variation, as you can see. So from the bottom, because this is simply supported beam, we have sagging moment here. So from the bottom, it starts coming back to 0 position here. This is the location of the neutral axis, and above that you can see a nonlinear variation of strain. Now, this strain distribution will govern what, if you recall, in case of a shallow beam, we identify the location of the compressive force and the tensile force, right? Then we balance these two forces in such a way that we can find out the location of the neutral axis, which is in between. Now, in case of deep beam, the neutral axis is somewhere here, but it is very difficult to actually find out the exact location, because for that we have to apply a different load transfer mechanism, which is primarily through arching actions and start and tie mechanism. Now, this is the fundamental difference between a shallow beam and a deep beam. So from shallow beam to deep beam, the main first difference is basically the way we evaluate the neutral axis. Now, once we evaluate the neutral axis, our main objective is to find out this lever arm, right? So this lever arm, that is the distance between the tensile and compressive force, dictates the sectional capacity. Now, for deep beam, Indian codal provisions are there to find out this lever arm directly using some empirical formula. So it grossly simplifies our workload. Otherwise, we have to apply the strain variations, and from that strain variation, we have to find out exact location of the neutral axis. Now, IS 456 clause number 29.2 actually dictates the lever arm for simply supported beam and continuous beam, as you can see on your screen. So Z is the lever arm. So this is the lever arm here, is equal to 0.2 times L effective plus twice D, when L effective by D lies between 1 to 2. And if it is less than 1, then this lever arm is 0.6 times L effective, right? So when we start the problem from the geometry itself, we can find out the L effective, and we can select a D in such a way that the problem is for a deep beam. And then from that information, using this empirical formula, we can find out what is the lever arm. And the moment we find out lever arm, actually the problem is very simple, because our remaining task is to find out the amount of steel that we are going to provide. And this fundamental step is grossly simplified by this Indian codal provision. For continuous beam, the same lever arm is 0.2 times L effective plus 1.5 D, when this L effective by D ratio is between 1 to 2.5, and if it is less than 1, the lever arm is 0.5 of L effective. Okay, so you see, you can easily evaluate this and you can go for the estimation of the steel. Okay, so particularly this clause 29.2 simplifies the design of this deep beam to a great extent. Now, once we find out the steel requirement, you will see there is some special provisions that we have to follow. It is not like shallow beam, that we'll take it up in a minute. But the first thing is to be noticed here is that the lever arm for this section is given by this empirical formula, right? Okay, so now let us go to the reinforcements, because once we find out lever arm, we can easily evaluate the reinforcement. But before we find out reinforcement, we take an example. Let us first see what are the codal provisions given, and then we'll solve one example. Now, for a continuous beam, you have already noticed there will be sagging and hogging moment, and in case of a simply supported beam, there will be only sagging moment. Now, the first thing is positive reinforcement as per clause 29.3.1. The tensile reinforcement required to resist positive bending moment in any span of a deep beam. For that, we have two different options. shall not be curtailed at the support. So this is very important. It should not be curtailed at the support. The steel shall be embedded beyond the face of each support so that at the face of support, it shall have a development length not less than 0.8 LD. Recall, we have already evaluated development length as per clause 26.2.1, which is 5 times sigma s divided by 4 tau BD. So you are all familiar with, we have already discussed this in detail. So for every bar, we need to find out the development length and we need to satisfy this curtailment requirement when we provide the positive reinforcement. Now, the reinforcement shall be placed within a zone of depth equal to 0.25 D or 0.05 L effective. This I will show you when we will detail a section. Okay. So, we are talking about positive reinforcement. Once we identify positive reinforcement, then the reinforcement shall be provided within a zone. So, we are talking about a zone of depth. This is important in case of a deep beam. Earlier, if you recall, the moment we provide this reinforcement, we provide it in a single layer, right? Like this. Here it says that we have to provide it within a zone. So there is a zone here. So we have to provide, we have to distribute all this within this zone. Okay. And the depth of this zone is specified. We'll see there are other zones also. So for positive reinforcement, it is 0.25 D or 0.05 of L effective, which is greater and adjacent to the tension phase of the beam. Okay. So we have to find out these two possibilities, and greater of that we have to consider, that is the zone in which we have to uniformly distribute. Now let us move over to negative reinforcement, because in case of support we will have negative reinforcement, and for that the clause number is 29.3.2. First point is termination of reinforcement. So half of the negative reinforcement may be terminated at a distance of 0.5 D from the face of the support, and the remaining reinforcement shall be extended over the full span. So this is important. If we go for curtailment, then we actually can go for a curtailment after 0.5 D from the face of the support, and that too half of the negative reinforcement. Okay. So curtailment option is clearly defined because the negative reinforcement at the support is not required in the midspan, and therefore this provision is given. But we can only curtail half of the reinforcement. Now comes distribution of the negative reinforcement. When the clear span divided by overall depth is less than 1, the negative reinforcement shall be evenly distributed over a depth of 0.8 D from the top tension phase at the support. When the span to depth ratio is in the range of 1 to 2.5, the reinforcement shall be provided into two zones. So this is important. You see, I earlier said that there are multiple zones in case of deep beam. So if we satisfy this second category, then we have the first zone. It has a depth of 0.2 D from the top tension phase. So from this top tension phase, we have, this is 0.2 D. So that is the first zone. And within this zone, it shall contain, this is the amount of steel. So we can find out the AST requirement at the support. Then this fraction shown here, this amount of steel we have to provide in zone 1. So this is zone 1. Then the second zone, a zone measuring 0.3 D on either side of the mid depth of the beam, which shall contain the remaining reinforcement for negative moment and shall be evenly distributed. So this is the first zone, and for the second zone, the zone measuring point 3D on either face. So here is the second zone, right? And the point to be noted, this much of steel we provide in the zone 1, the remaining steel we have to evenly distribute in this second zone. Then there are vertical reinforcement. Recall we provided stirrups in case of shallow beam. Here 29.3.3 actually gives us the guideline how to provide this vertical reinforcement. If loads are applied at the bottom of the beam which induce hanging action, as in case of bunker walls, bars or suspension stirrup shall be provided to carry all the loads. Okay. Then side face reinforcement, that is the next clause. Side face reinforcement shall be provided both in the vertical and horizontal directions at a spacing not more than 3 times the width of the beam, 450 millimeter, whichever is less. Okay. So side face also we have to provide additional reinforcement, and then comes the minimum thickness. The minimum thickness of a deep beam should be based on the two considerations. Firstly, it should be thick enough to prevent buckling, because if we have a beam of this and if we have the same beam of this geometry, their buckling behaviors are all different. So just imagine if we have a skinny beam, it is prone to buckle. So the empirical requirement to prevent buckling is here d by t is less than 25 and L by t is less than 50, where t is the thickness of the beam. Secondly, the thickness should be such that the concrete itself is capable of carrying a significant amount of shear force acting in the beam without assistance of any steel requirement. This is important. In fact, when we design shallow beam, if you recall, first we check the capacity offered by the concrete itself. Then, if the need be, the additional requirement we commit with the stirrup. Here also we will design the concrete in such a way that the concrete section here should be sufficient enough to withstand the major part of the shear requirement, right? Okay. Now with that, let us take an example, because that will clarify all the doubts how to estimate the steel and how to provide them. So the first example is a continuous beam. As you can see, we have a continuous beam here, and this continuous beam has 3 spans. So the first one is 11 meter, then 12 meter and 11.5 meter. We purposefully keep this varying so that we can see the difference in moments, how to evaluate as per IS codal provisions, right? Now the width of the support is given. So width of the support is 250 millimeter. Now this support width can actually vary. The depth of the beam is 5.2 meters. So this depth of the beam is 5.2 meter. Remember, this is capital D, not small d. Beam attached to RC slab monolithically at the top, which is fine. So imposed load is 12 kilonewton per meter, that is coming from the slab. Nominal cover is given 25 millimeter. Now our task is to estimate the reinforcement. So first we, as usual, evaluate the clear span. Now for the clear span, it is the distance between the two supports. So we have maximum center to center distance is 12 meter minus the support width is basically the clear span. So L effective is minimum of 12 meter, which is the largest span, and 1.15 times the clear span, which is we have already evaluated. So this is 13.5125 meters. So L effective what we get is 12 meter in this case, right? Now L effective by D, so 12 by depth is 5.2 meter. So L effective by D is 2.307, which is less than 2.5, and hence we have our deep beam. Once we calculate the L effective and check whether the condition for deep beam is satisfied or not, next task is to calculate the bending moment, right? So for bending moment, again, IS code provides this clause 22.5.1 that gives us moment coefficients to directly find out the bending moment at midspan and support without going for a detailed structural analysis. Now, the span length do not differ by more than 15%. So this is the requirement for using this moment coefficient. So we have 12 meter here, maximum span. Then other two spans are 11 and 11.5 meter. So the largest span, 12 meter, divided by the shortest span is 1.09. That means 9% variation we have. So we can safely use the moment coefficients, right? Now, this is a continuous beam. So we have to find out the moments at different sections. So for that, we prepare a table, and before that, we calculate the load. So the first load is self-weight, that is the dead load of the beam. As per IS 456, it is 25 kilonewton per meter cube. So we get the dead load for this particular beam is 32.5 kilonewton per meter. Then we have to find out the design load, which is 1.5 times the dead load plus the imposed load, which is 12 kilonewton per meter, that is coming from the slab monolithically casted with this beam. So ultimately, we get a UDL of 66.75 kilonewton per meter. So as you can see here, this is the UDL, 66.75 kilonewton meter. And you can see the supports which are marked A, B, C and D. Now, as per the guidelines given, codal provisions, we use moment coefficient to find out the moment at different locations. So we have three span AB, BC and CD. And the span lengths are 11, 12 and 11.5. Then for every support, we check for every span. So say this span is AB. So moment at the left support, we have 0 obviously because this is simply support and that is the extreme end. The other support we have 110 times omega u times the length square, which is 11. So 11 square. So we get 807.675. Similarly, for other supports, we find out what are the bending moments, right? And the extreme right support, again, it is 0. So these are the support moments, as you can see, support, left or right. So for every span, we find out left support and right support and their bending moments. Then for every span, we also find out the span moments, which is 1 by 12 times WU times L square. So for the first span, the span moment is 673.0625. For the second span, it is 600.75 and the last span, it is 735.64. So for the support, the maximum bending moment that we have is 961.2 kilonewton. So we are going to design the cross section based on this maximum moment, right? So next is we have to find out the lever arm because that we are going to use to estimate the amount of steel required. So for that, first we calculate lever arm, and I have already explained that for lever arm we have a empirical formula because this is a continuous beam. We have 0.2 times L effective plus 1.5 D, and this lever arm for our problem is 3.96. Then once we calculate lever arm, we can use this expression mu divided by 0.87 Fy times Z is the AST required. So for this problem, AST required is 672.28 millimeter square. So what we do, we provide 16 diameter longitudinal bars and 8 diameter stirrups. So let us assume that, let us see whether that will satisfy the requirement. So the number of bars required, 4 numbers. And then clear span by overall depth, that is L by D ratio is 2.26. So this beam, this D beam, we can distribute the reinforcement as we have obtained from this expression, right? Now for the other part, when we go to the support, we have to provide the reinforcement in different zones, right? So zone 1, depth is 0.2 D, D is 5.2 meters, so this depth is 1.04 meter. Then next is we have to find out the coefficients. That alpha, this is the coefficient of steel. That means this amount, this percentage of steel will provide in zone 1. And this alpha is 0.5 times L by D minus 0.5. So it is 0.88. That means 88% of the negative reinforcement we have to provide in zone 1. So how to find out the negative reinforcement? For that again AST we can find out using the same expression that we will do in a minute. But AST minimum is again 0.85 B times D divided by Fy. Right. Now this D is effective depth. So we evaluate effective depth for this problem. And here we have 4663.5 is the effective depth, and we can find out AST minimum, which is 2388 millimeter square. Okay. So now let us provide reinforcement in zone 1, which is 88% of the reinforcement required. So we provide 88% of the reinforcement that we have evaluated. So this is 2102. Let us try with 16 diameter bars. So how many bars we require? We require 11 number of bars. So for zone 1, which is the top point 2D, there we provide 12 number of 16 diameter bars, arrange them in 4 layers. We will show you the detailing in a minute. So we have 3 bars in each layer, and then spacing for them is 335 millimeter. So when we will go for detailing, we will use this information. I will show you how to provide these bars when we draw the cross section. Then next is check the vertical reinforcement spacing. So for that we have a dedicated clause 32.5b. So the spacing should be less than minimum of this 3b or 450. We have already discussed. So in this case it is 450. So our provision of 335 millimeter is less than 450 millimeter, which is okay. Now let us come to the zone 2. For zone 2, it is 0.12 times the steel, which is 286 millimeter square. So this is a very small amount considering the extent of 0.6D. Hence we have to provide side reinforcement as nominal RC walls. And for that the clause is 32.5C, and here the amount of steel for this purpose is 0.2% of the cross-sectional area. So what is 2600 millimeter square, which is far more than what we estimate here. So for that again we provide 16 diameter bars. How many bars we need to provide? 13. Now here, if we provide 13 number of bars, you can calculate the spacing of the bar, which I keep it as a home task. So 13 number of bars you have to provide in 2 or 3 layers. Say you provide in 3 layers, so 5 bars in each layer, and you can find out the distance between the 2 bars, and you will see here the minimum requirement you have to satisfy. It will actually violate. So what we do ultimately, we provide 21 number of bars. 7 in each layer, we will provide 3 layers. I will show you the cross section in a minute. So 16 diameter bar, 21 of them in 3 layers, right? As side face requirements over this zone is 0.6D. The spacing is with these 21 bars is 3120 divided by 8, which is 390 and less than 400 millimeters. So this is okay. So now you can see the steel provided. So we have, this is our zone 1. In zone 1, which is 0.2D, that means 1.04, we have 12 bars here. So 12 bars, 12, 5, 16. Then we have zone 2. So this is our zone 2, where we have 0.6D. 0.6D is 3.12 meter, and there we provide 21 bars. As you can see, we have in 3 layers 21 bars of 16.5. Of course, you can try with 25 bars. That will reduce the number of bars, but accordingly you have to check the spacing also and then provide adequate number of bars. That is the liberty every designer has. So we provide here 16.5. It can be 25 or 25.5 also. Then at the beginning we have evaluated these bars at the mid span, which is up to 0.7 meter. I will show you that in a minute. So that provides the bar in zone 1 and zone 2. So for the mid span bars, which is at the bottom, I just showed you in the cross section. So it is AST equal to mid span moment divided by 0.87 FYZ, which is 512 millimeter square, and there is a minimum requirement of steel which is 2388 millimeter square. So what we do to provide this much of steel, we provide again 16.5 bars, and we have to provide 11 number of bars. That is the requirement. So we provide 12 number of 16.5 bars, and which is provided here. So we have 12 number of 16.5 bars at the middle. So what we do, we provide in 3 bars in each layer. So there are 4 layers of bars, altogether 12 bars, and the spacing between these bars you can evaluate, which is 220 millimeters, which is okay. Then we have to provide vertical and horizontal reinforcement. So as per IS provisions, it is 0.12% of the gross cross-sectional area per meter length. So we get it as 300 millimeter square per meter length of the beam. So let us provide 8 millimeter diameter bars, and we provide a spacing of 300 millimeter center to center on each face. Okay. So if we see the bars, you can see it here. So here is the point 2D zone 1. Then we have the zone 2, which is here, and we have to provide the bars. So the detailing is here. Now here actually you see we provide 16.5 bars, and in my estimations I did not provide any curtailment of bars. If you provide, these are actually additional bars. I have just shown you. If you go for curtailment, then recall from the face of the support you can go up to 0.5D and curtail. So these bars are actually not there because for the time being I did not provide any curtailment. So if you provide curtailment, so you show bars like this, half of the bar at the tension zone you can curtail, and it should go up to 0.5D, right? So our depth is 5.2 meter, so up to 2.6 meter you can go. That will be a provision you can have, but for the time being, just to show you whatever we have designed. So 12 number of bars we have at the tension zone. Then in zone 2 we have 21 number of 16.5 bars, 3 bars in each layer. Then in the mid span we have 12 number of 16.5 bars, 3 bars in each layer. And then we have vertical side face reinforcement, which is 8.5 300 millimeter center to center. So that completes the design with only one additional thing. If you wish, you can go for this curtailment, which is actually shown here, but we continue these bars. So these curtailments are not, these bars are not there. If you plan for curtailment, you can show the curtailment of the bars like this. Okay, this is just for your information. And in case of curtailment, you can go only up to 0.5D. So that clearly shows you how for a deep beam, you design the bars, you provide the bars in different zones, what are the different types of bars that we need to provide, and accordingly you can detail the cross sections. So go through this derivations and notes, and if you have any doubt, do let us know. In the next class, what we'll do, we'll solve one simply supported beam. We'll design and detail it out, right? In the meantime, you just go through this example, and if you have any doubt, drop an email. We will clear your doubt. Thank you very much.